A URL shortener looks like a weekend project, but building one that handles hundreds of millions of redirects a day, each in under 10 milliseconds, is a genuinely interesting distributed systems problem. The job is simple. A creator pastes a long URL and gets back a short code like shortener, and any visitor who clicks it lands on the original page. The hidden difficulty is the read-to-write ratio. For every person who creates a short link, there might be 100 or 1,000 people clicking it, so the system has to be aggressively read-optimized from the very start. All traffic, from both creators and visitors, enters through a load balancer. This single front door lets us add or remove API servers behind it without the caller ever noticing. Behind the balancer sits stateless API servers. Because no server holds any in-memory session data, any server can answer any request. That is exactly what makes adding more of later completely seamless. The API layer connects to three components: a key generator that mints fresh short codes, a database that permanently stores every mapping, and a cache that absorbs the vast majority of read traffic. A short code is just a compact string, 7 characters picked from 62 possible values. The digits 0 through 9, plus all 26 lowercase and 26 uppercase letters. 7 characters from 62 gives over 3.5 trillion unique combinations, far more than any real shortener will ever exhaust, even at the scale of billions of stored links. The cleanest approach is a shared counter kept in the database. Each new link claims the next available number, and the API encodes that number into the 62-character alphabet. 2 requests can never produce the same code. A monotonically increasing counter also keeps database inserts in order, so index pages stay dense and queries stay fast, a detail that matters a great deal once the table reaches billions of rows. Here is the full write path. The creator submits the long URL, a TP's, example.com article, and the request travels through the balancer to an API server. The API calls the key generator, which bumps the shared counter and encodes it, producing the short code Xylo. The API writes one row to the database pairing that short code with the long URL, then returns the finished short link to the creator. Write path complete. The read path starts when a visitor clicks short.ly/x7k2. The browser sends a lookup request through the balancer to whichever API server is free. The API server checks the cache first. If the code is already there, it gets the long URL back in a fraction of a millisecond. This is the hot path, and it handles the overwhelming majority of traffic. On a catchy hit, the API sends back a redirect pointing to TP's, example.com article. The visitor's browser follows it, and the whole round trip completes in the tens of milliseconds. On a cache miss, the first time anyone clicks a brand new link, the request falls through to the database to fetch the long URL. After the database returns the URL, the API writes it into the cache. Every subsequent click for that same short code is served from memory. The database is never touched again for that link. Because the API servers hold no state, you scale read capacity by simply adding more of them behind the balancer. The cache means the database rarely sees the full request volume. The main trade-off is in the key generator. A single shared counter is collision-free but becomes a write bottleneck at extreme scale. The fix is range pre-allocation. Each server claims a block of 1,000 IDs at once and mints codes locally, with no coordination needed on every single write. With range pre-allocation, the key generator is almost never on the critical path. Collisions remain impossible, and the system scales out horizontally without any coordination cost on the hot path. The cache works best with a time-based expiry. Popular links stay warm and rarely clicked links fall out naturally, keeping memory usage predictable, even as the total number of stored mappings grows into the billions.